Core Curriculum Pedagogy, Part B, Mathematics and Science. This presentation will discuss some of the organisational issues and pedagogical decisions linked with cross-curricular practice, along with my own experiences from school. I will also explain how ICT tools could be used to support cross-curricular learning. For the purpose of this presentation, cross-curricular learning will be defined as when the skills, knowledge and attitudes of a number of different disciplines are applied to a single experience, problem, question, theme or idea. Cross-curricular teaching and learning is based around a constructivist approach, as constructivists contend that students learn through connections formed between prior knowledge and new experiences, and as connections arise among existing ideas. Piaget coined the term accommodation and assimilation to explain the way that children learn by making and understanding errors. Vygotsky and Bruner believe that children learn best through social interaction and the support and guidance of a significant other scaffolding their learning. These social experiences allow the child to make sense of the world through linking their previous gained knowledge with the new ideas of their peers or an adult in their zone of proximal development. The Haddo report focused on child-centered learning. Alexander noted that the report did separate knowledge from experience. Knowing and doing should not be separated, but instead integrated through purposeful activities and making connections. The Haddo report was further developed by the Plowden report, whereby Lady Plowden suggested that in order for children to problem solve, they need to be able to make links between their previously existing knowledge, interests, new ideas and concepts. Therefore, there should not be a divide between the subjects in primary schools. Contrary to this, the Education Reform Act led to the first national curriculum, which set out single subject teaching. Young children learn best as a result of play and exploration, active learning, and creating and thinking critically. These characteristics of learning allow children to accommodate and assimilate new information by problem solving. Common themes in the programs of study in the national curriculum for mathematics and science include problem solving, reasoning, classifying, identifying patterns, grouping, and sorting. Children should apply their mathematical knowledge to their understanding of science, including collecting, presenting, and analysing data. Children acquire these skills based on the similarities and differences they have observed. Myers and Nicol collated a review of literature of potential benefits and barriers to integration, including students gaining interconnected knowledge of mathematics and science, a deeper understanding of abstract mathematical concepts gained through visual scientific examples and quantitative explanations, and purposeful learning that is relevant, practical, and can be applied in real-life situations. Some of the barriers were the lack of time to research the standards of learning for mathematics and science, teachers' lack of in-depth subject knowledge in order to successfully make the necessary links between the two disciplines, school structure barriers such as the timetabling of students and teachers, location of the classrooms, and the lack of materials. They conclude that the integration of mathematics and science would result in positive educational change for schools and students. They suggested that the best practice for cross-curricular learning could be extended from Lemann's ideas for action. One of his recommendations focused upon helping trainee teachers build upon their understanding of how cross-curricular learning can meet their individual curricular objectives. By following Lemann's suggestions, it may be possible to overcome the barriers to integration and to see positive results. Voss et al. Carried out a study in order to determine the degree of the similarities between the standards for learning mathematics and science laid out in these documents and whether children learn mathematics and science through similar processes. The researchers identified that there were 51 initial descriptors that made up the 10 learning processes of the standards. Their findings showed that of these 51 descriptors, 41 of them were shared between both subject areas of mathematics and science. Morrison and McDuffie carried out an investigation to determine whether merging scientific and mathematical instruction improved undergraduate teachers' understanding and skills used to teach data collection, analysis, and display methods. Their findings demonstrated that teaching mathematics and science alongside each other promoted a better understanding of both subject areas and highlighted the connections and commonalities between both areas. However, as with many studies, these findings may not be generalizable, as they may have been specific to the study that the participants completed. There are many mathematical skills which can be transferred over to scientific inquiry, as shown here on the slide. Mathematics is important in investigation to allow children time to record their findings using standard measurements, creating a bar chart or line graph, and taking repeat readings and working out an average. Brown established 3 strands of data handling, best implemented through play, For example, a child could collect the data for the number of different animals they can find around the classroom and then record it in a tally chart or pictogram. I have observed this particular strand of data handling during my teaching practice and found it to be very successful. This is also supported by Harlan, who states play enables children to develop their problem-solving skills through first-hand experiences and developing abstract symbolic thinking skills, questioning and finding out about their environment and the objects around them through interaction and exploration. It is the role of the teacher to determine whether mathematics and science should be taught alongside each other, or whether mathematics should precede science in order to allow children time to develop the strategies and skills needed to carry out practical work such as statistics, measurement, and basic counting skills. Mathematics and science could also be taught following a topic, for example, toys and games. This is referred to as a thematic approach. Examples of activities which I have observed during my teaching practice relating to mathematics and science are testing how many coins can a paper boat hold, recording the time taken for chocolate to melt, making Rice Krispie cakes using the amount and weights of ingredients, testing the stretchiness of socks by measuring their weight or length, measuring children in hands or using measuring instruments, and measuring how tall is the elephant in Unifix cubes. The Three Wise Men report of Alexander et al. Criticized thematic approaches due to the lack of depth and skill development. Their findings demonstrated that thematic schemes of work took away from the main focus of a logical and consistent approach to transferring subject knowledge. Therefore, the theme was distracting from children's progression from one age-related stage to the next. It is not always possible to make meaningful links between mathematics and science. Therefore, it is paramount that whichever approach used provides opportunities for making children's learning relevant, engagement in real-life situations, making connections, guided learning based on commonly held misconceptions, developing specific skills, and providing lots of opportunities for inquiry. There may be issues when teaching mathematics and science in a cross-curricular way, as practitioners may lack the pedagogical knowledge to enable them to link the subjects effectively, providing authentic context where pupils can develop their subject knowledge. Berlin and White found that the connections between science, technology, engineering, and mathematics can result in higher achievement, more positive attitudes to learning, and reduced planning time. Computing has deep links with mathematics and science in the new national curriculum. These can be portrayed by using interactive whiteboards to display simulations of phenomena that cannot readily be seen through direct experience in the classroom, for example, looking at different types of animals in their natural habitats, as well as the use of a digital camera to record children's findings from investigations in science. The B-bot is a transitional robot that allows children to develop abstraction of mathematical concepts from action to representation. B-bots allow children to use directional and positional language. An activity would be to program the B-bot to collect the objects in the order of the life cycle of the frog. Metal detectors could be used to develop scientific skills to identify objects made out of metal. An example of an activity using a metal detector could be to laminate 6 plain shapes, hold a piece of metal underneath one of them, and ask the children to locate it using the metal detector. McAllister, Dunn and Quinn examined teachers' attitudes towards the use of computers in teaching mathematics in the primary school classroom. They found that computers could be used as a tool in supporting and enhancing students' learning, as well as a tool for teaching. To conclude, a cross-curricular approach enables pupils to apply their previously existing ideas and skills to real-life situations. By combining discrete knowledge of mathematics and science, the child is able to gain a deeper understanding of abstract mathematical concepts through visual scientific examples. Therefore, cross-curricular teaching and learning would be extremely beneficial in combination with some discrete subject lessons, which cover differences in mathematics and science which do not lend themselves to a cross-curricular approach. However, there are some barriers to a cross-curricular approach which need to be overcome in order for this to be successful. These organisational issues are a lack of time, perceptions of teachers and parents, and school structure. These can be overcome through teacher training and continuous support. This would actually cut down on planning time, informing the community of the value of the approach and ensuring that the classrooms for both subjects are located in a close proximity to each other. Pros outweigh the cons for using a cross-curricular approach to teaching mathematics and science. I believe that following Lemann's recommendations, there needs to be an educational reform for integrated mathematics and science pedagogy. Cross-curricular learning could result in positive educational change, which would set children up with the skills they can apply to real-life situations beyond their school years.